when we are going to consider the synthesis design flow, the first point what we have to remember is, first we have to describe the design in a RTL description. So this description must be very clear. Based on this only, the translation will be done. What translator will going to do? It will going to convert the design whatever we have described. It will going to generate the information or database that which components are required to implement which particular circuit. All these details will be given by the translation, and that will be in a unoptimized representation. Why it is called unoptimized representation means, generally it will going to give the information regarding which components it has to use, but there will be no idea that with using minimum number of components how we can able to perform the given function. So that is the reason it is called as unoptimized representation. When once this representation is received, what logic optimization will going to do? It will going to convert the given information into an optimized circuit. As I told in the last class, if you want to perform any 10-bit addition, or if I want to perform 10-bit multiplication, so considering 1-bit multiplication 10 times, or parallelly considering 10 1-bit multipliers, there the complexity of the circuit may be large, making interconnection and all. There may be some other circuit which uses minimum components less compared to the existing circuit, and even it can give the same results. So that is known as optimized circuit. Like this we are going to consider logic optimization. When once the optimization of the circuit has been done, so till now it will not going to consider any constraints like time constraint, area constraint, or the power constraint. All those things will not be considered up to logic optimization. But when it comes to technology mapping optimization, here what it will going to do means, it will first check what are the available leaf cells present in the library, means for which vendor this logic circuit is designing. So from that vendor, which gates they are considering, and what are the leaf cells and its corresponding timing constraints, all these things it will going to collect the information along with the optimized circuit. Then based on the available leaf cell, once again the circuit will be optimized depending upon the vendor's library, technology library. And finally we are going to get the optimized gate level representation. And now let us see how this can be considered when we are going to consider an example. So first let us consider an example of 4-bit magnitude comparator. In this 4-bit magnitude comparator, what is the design specification that are provided? These are the 6 design specifications that are provided. That is, the name of the design has to be given. So here magnitude comparator is taken as name of the device, and then what are the input ports and its data size. All these things we have to mention, and how many output ports are there, that we have to mention, and when the output port should be active and when the output port should be zero, means when the output is high and when the output is low. All these conditions are mentioned. So here it has been mentioned that we are considering 2 4-bit input, and also we are not considering any high impedance or unknown value as a input for A and B. Directly we are considering either 0 or 1 will be the input. In that fashion we are going to design the program, and then we will going to declare the output, that is A greater than B will be high only when A is greater than B, otherwise this particular output will be low. So like this we will going to specify the specification, required specification, and afterwards what we are considering is the circuit must give the output as fast as possible. Means we are not mentioning any area constraint, we are just considering as soon as we give the input we should get the output. So this is considered as speed consideration, or the time constraint. Okay, like this, because when we are designing any circuit, we will be keeping at least one particular criteria, at least it should work fast, or it has to use minimum resource, all these things. So here mainly we are considering to get, we have to get appropriate output as fast as possible. So this is what it has been mentioned. These are the 6 specifications mentioned, and according to that the corresponding RTL program has been written. So what is the corresponding RTL program? Here we are indicating we are doing module definition by the name, magnitude comparator, and we will mention all the IO ports, and exactly we have to specify the size. Okay, so the size of the input output ports are specified exactly, and then we have mentioned when the output should be high and when the output should be low. All these things we are going to consider. This is RTL description. And afterwards, uh, what the next process the synthesis tool will going to do, based on the description, first it will going to check what are the technology, what are the components available in technology library. Means when a vendor has given this particular design or specification, then according to the vendor's technology, which particular cells are available to make the circuit. So that is why it will going to check the corresponding vendor library. Based on that, it will going to understand what components are available, and that library cell should be in a format that can be understood by the synthesis tool. Then only it will come to know which components it has to use for the design. So like this, here these are some of the examples how the technology library cells can be, like how we are using the primitive gates and NAND. They are all the library cells that are already defined in the library, so directly we are using, isn't it? In the same way, here also we can able to consider the technology dependent library. And when we are going to consider the technology dependent library, in that case, while building the library, vendor will going to consider the following specification, that is functionality of each cell, its timing constraint, means how much time it will going to take to give the output for a change in input, and how much area it will occupy, how much power dissipation. All these things will be decided by the vendor, because he is building the technology library. So what he will going to do, he will going to have these constraints, that is nothing but according to the specification. First we are going to get the unoptimized circuit, and then what this logic synthesis tool will going to do, it will going to, yeah, it will going to synthesize, means based on the description and the available technology library, it will going to generate an optimized circuit. When once the optimized circuit is generated, then the corresponding uh, connection will be established. So this is known as final optimized gate level description generated by the synthesis tool. Okay, and here connections are made with by name, like port connections. Usually there are two types of connection by order and connection by name. So here we are going to make connection by name, and this is how we can get the corresponding program with respect to RTL level description. So in user has given this description, but what actually the synthesis tool will going to do, it will going to give this description, and it will tell how the corresponding gates are interconnected and how this circuit will be generating the output for a given input. So like this it will going to tell the corresponding gate level description. Now when once we get the gate level description, what is the next thing? We have to verify whether it can be manufactured or not. Before manufacturing, we have to verify the functionality. So while the designer, while giving the RTL description, he will going to verify the functionality by doing simulation. Now when once the synthesis has been done, once again it has to check the corresponding circuit whether it will going to give proper output or not. So for that, what we are going to do, we will going to perform verification of the RTL gate level description. So in this, what we are going to do is, here a stimulus program is written. Why we are going to write stimulus program? In order to give input and check the output whether we are getting proper output or not. For that reason we are going to write the stimulus program. So for the RTL description that is given by the designer, this simulation stimulus we are going to consider. But for the gate level netlist created by the synthesis tool, the same inputs we have to give, which inputs we have verified in the RTL simulation. Here also we should verify with the same inputs, and what output we got in the RTL description, the same output we have to get in this particular simulation also. So that is why here this is the stimulus for magnitude comparator. And next we are going to consider the simulation library. So why we are considering the simulation library means, see, a common input has to be given and tested before generating the gate level netlist as well as after generating the gate level netlist. As a result, stimulus program will not going to change. But while executing this stimulus program, we have to consider the corresponding library, technology library given by the vendor. While considering only RTL description, here there is no time constraint or any other constraint. It is not with respect to any particular technology. So as a result, it can consider any simulator and it can verify the functionality. But when once we consider synthesizing, there we have to select a particular technology because we want to generate a circuit such that it can be fabricated in a specific technology like 90 nanometer technology or micrometer technology. Like this we are going to consider. So in order to consider that, we need a corresponding vendor's library, technology library. So what he will going to do, he will going to give a technology library. But while compiling this or while executing stimulus for the gate level description, we have to invoke the library. In order to invoke the library, what we are going to do means, here we are going to consider the corresponding -v. So this will going to invoke the corresponding library, and here we have to consider which particular library it has to invoke. So as a result, it will going to connect that library for the stimulus program while applying stimulus for gate level description. But while applying stimulus for RTL description, we are not invoking directly, only stimulus is considered. Now what is there in the corresponding library? So inside this library, how every gate will be tested, so that, or how the definition of every gate has been written. So for that we are having an example of AND gate, two input AND gate. So here we are having one input as IN0 and the another input as IN1, and here the one output, that is out. And here what we are considering is IN1 is assigned to out, means whenever an input is given for the port IN0. Okay, so in that case it will going to consider this much time of rise delay and this much time of fall delay. So here we know that we can express the delay in terms of rise delay and as well as fall delay if there are only two values. If there are three values, we can consider rise delay, fall delay, turn off delay. But here only rise delay and fall delay is specified. And when I consider rise delay, again I can specify minimum rise delay, and then I can consider the corresponding typical rise delay, and then we can consider the corresponding maximum rise delay. Okay, so as a result we will be having minimum, typical and maximum. These values will be there. So for every gate the vendor will going to mention how much minimum delay it can take, rise delay it can take, and typical or maximum rise delay. Similarly for fall delay he will going to mention for every pin. Okay, and whenever an input is connected to this particular pin, in that case if there is any change in the value, either it has to change from logic 0 to logic high or logic high to logic 0. So in such case it has to consider at least this much delay. Okay, and then uh, we are going to consider the executable statement. So here specify means he is indicating it has to consider delay within this range only, it cannot go beyond the given range. And afterwards he will going to write the corresponding executable statement. So like this, for every gate definition will be there in the library. According to that it will going to take the corresponding delay and it will going to execute. And when once it has been executed, then we will going to check what was the output we got for these inputs in RTL description as well as in gate level description. If both the outputs are same, then the design is correct, then it can be considered for implementation. If there is any mismatch in the design, once again we have to redesign, and after redesigning once again the process repeats, means we have to synthesize and then once again we have to verify whether both the results are same. Until this condition satisfy, the synthesis process will not going to complete. This is what your CAD tool will going to do. So when we are going to consider the corresponding Xilinx program, there you might have seen the Xilinx software. And so I'll just share this screen. So when we are going to consider this Xilinx software, so here let us consider the example of this demultiplexer, or let me consider the example of half adder. Okay, here with delays I have taken. Let me take ripple carry counter. Okay, so in this we are considering an example of ripple carry counter. So till now what we have done is we have done simulation, isn't it? So here we had taken, I mean we have mentioned the specification required. According to that this RTL description has been written, and we used to check the functionality of the description using the simulation. There we are not specifying using which particular technology library we are considering. Okay, in order to implement this circuit, here we are going to select implement. So in this window we can able to see on the upper left corner view. So till now we have selected simulation, now we will going to select implementation. When once the implementation is selected, then whichever the circuit we want to build, that should be considered as the top module. So because that only that particular beyond other circuits are present inside that circuit. Okay, so that is why it should be set as a top module. So when we are going to set that particular set as a top module, you can able to see this type of symbol. So where it will show the hierarchy symbol. So top module, inside that another sub modules. So like this it will going to show the hierarchy symbol. And now below that wizard we can able to see no processes running. So this process wizard is there. Here you can able to see under the synthesis link we are going to perform check syntax. After performing the check syntax, if there is no error, then we can able to simulate. So that indicates that we can able, our program can be tested using the simulation. When once we are getting the correct output, then we will go for synthesis. When we select synthesis, what synthesis will going to do? It will do the same process, means it will take the RTL description, it will going to generate the circuit based on the technology library defined, and then it will going to give the corresponding schematic. This we might have observed, that is how it will going to give the block diagram, and then inside that it will going to mention what are the corresponding lower blocks are present. And if we again click on this lower block, inside this lower block which other lower blocks are there, like this we can able to see the schematic diagram. Okay, this is only the schematic diagram. Technology schematic means it will going to consider actual, it depends upon the description given by the technology library. So here you can see the difference between the circuit what we have considered as a schematic diagram and what we have considered as technology schematic. So how actually each gate connection has been done by the synthesis tool using optimized circuit, how we can able to get the output. Like this we are going to get the technology schematic, means this is with respect to a particular. Here you can see in the hierarchy window, you can see that first we are selecting a particular IC, isn't it? So when we double click on the IC, which particular IC we have selected, it belongs to which family, all these things we have selected, isn't it? So the technology IC we have selected, it belongs to which family, all these things we have selected, isn't it? So the technology library defined for this IC is considered. Okay, using that it will going to generate this. Now suppose instead of Spartan 6, if you are going to consider some other circuit or some other technology family, so now in that case, so first let us consider how to synthesize using this particular device. Sorry, I have not saved, I think. So while considering, I have taken some other family instead of Spartan 6. Then let us save the connection. Okay, so now we can see the synthesis. Previously, a check mark was there, means it was synthesized with respect to Spartan 6 specification. Now some other IC I have selected. So once again, synthesis has to be done. So now let us consider the corresponding synthesis operation. So when once it has been synthesized, then we can able to notice the corresponding difference. If there is any difference with respect to the library provided by the Spartan 6 or other device. See here, again, schematic diagram will not going to change. Schematic will be same. And next, let us consider RTL technology schematic. So here, if I double click on this, here also we have got the same description. Okay, but what happens is the corresponding delays and all, there will be difference, but the resource used is same, because both the technology libraries may have common devices, like how an AND gate is present in all the technology devices. Similarly, there may be a T flip flop as well as the gate, clock circuit. All these things will be common. The default components will be present in the technology library. Apart from this, when we go for higher or any large circuit design, in that case we can able to experience that each technology library may not have same components. They will be differed either by the area or by the corresponding method how they will going to optimize the circuit. Based on that, there will be a difference. And here you can observe that we didn't change the RTL description, isn't it? Whatever the description we have written, we kept as it is. Okay, but only the synthesis, in order to synthesize, we change the corresponding technology library by selecting a particular device, and then it has been synthesized. So what it indicates is the designer job has been reduced. He does not need to worry about the technology library. He just want to take care regarding how best he can able to give the RTL description. If the RTL description is in a very optimized way, then still optimized circuit we can able to get. Suppose if it is not in a optimized way, in that case it will be difficult to get the optimized circuit. Okay, and one more example I want to show. So in this circuit we have considered T flip flop as well as D flip flop. So first let me consider the D flip flop, the basic. So here what I have mentioned is, I have clearly specified if reset is equal to 0, Q, sorry, if reset is active, Q will be 0, else Q will be equal to D. So like this, there is a clear description. If the description is not clear, so let me consider this example. If not of reset, Q will be equal to D. Okay, have just specified if reset is 0, in that case Q will be equal to D, but I have not specified what should be the output when reset is 1. Okay, only half of the description I have specified in D flip flop. So now let us observe that we can able to simulate this circuit, even though if we are going to make this small changes, but still we cannot able to synthesize. We will be getting error when we perform synthesis operation, because there we are not going to get the clear information. So here you can observe that we can able to get the output even though if we do not mention what should be the output when reset is 0. Okay, ಯಾವ್ದು select ಆಗಿದೆ. So here we can able to see what should be the corresponding output when reset is equal to 0. Means it will not going to show error while we are simulating. Now let us consider whether it will be synthesized or not. It has to show error because the description is incomplete. See, you can able to see this red symbol here, and also in the console we can able to see the synthesis has been failed. Why the synthesis has been failed? We can able to see the corresponding error. Assigned multiple single edge is not supported in the synthesis. All these things, these types of errors we are going to get. But the thing is, we have not done assignment properly. Okay, so in the previous case we return the same program, but here we have mentioned what should be the output when reset is 0 and what should be the output when reset is not 0. But here what we are doing is we are giving half description, complete description is not given. So that is why we can tell that all the design that can be simulated cannot be synthesized, but all the design that can be synthesized can be simulated. Means if we are able to synthesize, means we can able to generate the circuit. When circuit is generated, obviously we can check the output. The output may be correct or wrong, but still we can able to check and we can able to generate. Why? If we are not getting the required output, means some logic mistake is there. Okay, but still the circuit can be generated. So that is the reason we are going to tell that all the circuits that can be simulated cannot be synthesized. Okay, most of the circuits, around 90%, we can do both synthesis and simulation. But some circuits which are simulated and tested that they are working properly, still we are not going to get the output, means it indicates that there is a problem in the design or complete description is not provided, like how I gave an example of half description. So like this we are going to consider the difference between synthesis and simulation. Okay, so this is with respect to the synthesis part. And till now we have considered the corresponding modules: module 1, module 2, 3, 4, 5. So now all the modules with respect to your syllabus has been completed. But I just want to inform one more thing, that from next class onwards I'll do VHDL coding. So why we are going to consider VHDL coding, even though this may not be there in your theory, but in the lab program there may be a Verilog coding as well as VHDL coding. So why we are considering this VHDL coding means, like how we are having Verilog as a HDL language, similarly we are also having VHDL as a HDL language. There are two hardware description language. So V indicates for very high speed integrated circuit, and HDL is nothing but hardware description language. There are two types of language. And when compared to Verilog and VHDL, VHDL is very type specific, means exact precise data type and precise size of the data, everything you have to specify properly. Okay, but in case of Verilog it is not that much type specific. For example, in case of Verilog, if the output, let me consider the output D, if I mention the corresponding statement, like if I declare a wire, and here I'll mention the dimension of the wire is 3 down to 0, and let the name of the wire is D. And similarly we are going to declare other two wires whose dimension is 2 down to 0, A and B. Okay, now in this I can able to write the statement, that is assign D equals A and B. Okay, we will not going to get error, because even though there is a mismatch in the data size, we will not going to get error, because if this destination variable data size is larger than the input variables, then it will append zeros for the MSB and it will assign the value. But in case of VHDL it will going to show error, size mismatch error. So like this it is more type specific. And here while defining a particular wire or a register, we will not going to mention the data type, isn't it? Like whether it is an integer or a real number, like this we are not going to mention any data type. But when we are going to consider VHDL, every signal should be mentioned with the corresponding data type. Okay, so based on that we will going to consider how the programming can be done. And also one more thing, in case of this Verilog, if there is an integer number that cannot be assigned to a variable of type real. Okay, if I declare any variable integer A and real variable B, then if I want to write A should be assigned with the value B. So what happens if A is equal to 2 and let B be a in real number or a variable of real data type? So in that case, when I write B is equal to 2, so in the when I write B is equal to A, so which value will be stored in B? It will going to store the value as 2.0. Okay, means in this format only it will show store, but it will not show error. Even though this is integer and this is real, it will not show error in Verilog. But in VHDL, it is not like that. If it is a integer, the value should be assigned for integer only, not for a variable with another data type. So like this, we are going to consider more specific with respect to programming. Okay. The and best example what we are going to consider is when we are going to design a particular integrated circuits and all, we will going to consider two types. One is FPGA, that is field programmable gate array, and the another one is ASIC, that is nothing but application specific integrated circuit. Okay. So here, while generating the application specific integrated circuit, what we are going to do is, first we should able to find the corresponding optimized circuit, isn't it? So how to find the corresponding optimized circuit? See, by using FPGA, we will going to design the circuit. When once the design is working properly, then we can able to generate the application specific integrated circuit. Okay. So here what happens is, when we are making trial and error, every time we will not going to implement and we will not going to check. Only in the simulation we will going to identify, and then if it is working properly, then we will synthesize and we will going to check whether it works properly or not. All these things we will going to do. Okay. But when we are going to consider ASIC design, it will going to take more time, because it is designed only for a specific application. So while designing for a specific application, a more optimized circuit has to be generated, and a very minimum resource has to be used, and more optimized circuit has to be generated. And once it is generated, it cannot be redesigned. Okay. So as a result, in order to get a final output, first we will try the circuit in the FPGA. Like how when you are designing any particular project, or when you are designing any circuit in the laboratory, what you will going to do? By using some basic components, we will just make some trial and error, and finally we will come to get one final circuit. What are the required components needed, and how they should be interconnected? All these things we will going to finalize at the end. When once it is finalized, the same circuit can be used, isn't it? In the same way, while generating any particular design, we will be using FPGA. And when once the final circuit has been finalized, then it will be generated using application specific integrated circuit format. So there it will go for fabrication, and when once it is fabricated, it is specific for that application. And usually, one more thing, why it is called as field programmable gate array means, we can able to program the IC. Even the user can able to program the IC, means before manufacturing it is not programmed. Even after manufacturing, we can able to program and redesign the corresponding circuit required. As an example of Xilinx, so when we are going to consider Spartan 6 IC, so that IC operation can be programmed, means we are going to give input, we will do our own design and place that design in the circuit IC, and then we will going to check, isn't it? Means it indicates that we are programming the IC. So we are programming the IC as a user, but while manufacturing the IC, the designer has provided the option for user to program the IC. That is why it is called as field programmable gate array. Anyone can able to program the IC. But in case of ASIC, it is not like that. Only the manufacturer, that designer has to finalize the circuit. That is also one of the difference.